Hi, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning, and we are at the topic number 5, regularization, which is the techniques for preventing overfitting. So the subtopic is C. So this video 5C consists of kind of moderately difficult concepts, and the supplemental website used is www.ezmcq.com/goget. So the approach which we have adopted in this course is content delivery. And this content delivery is used by the leading learning management systems. And it has certain wonderful features. And there are millions of users of learning management systems which are based on content delivery. And here are some of the features which are there in such systems. And you can read through them and go through them. And these are the 6 features uh, which are used in the personalized learning management system, which are, for example, full scale text search, and based upon that text search, the Q&A of interest can be retrieved. Then it supports people who are visually handicapped, and it supports working in a small space to view, such as a smartphone, and the progress is tracked of the end user. And of course, there is MCQ based online testing and evaluation system, and so on. So there is a link here in the blue color, which is the link to these videos, which show you how to use that learning management system, for which the link is shown in green. And there are two basically approaches. One is the question and answer or Q&A based approach, and then is the traditional learning based approach. So the approach which we have adapted or adopted in this course is a combination of both. So Q&A is proactive, it is engaging, and it adapts to the user requirements, and of course it promotes thinking. And machines are not good at thinking, so we are ahead of them. It promotes that. So this is a blend of these two technologies, the approach or the methodology which we have been using in this course and other courses. So this is the breakdown of the topics which are covered in this course, Deep Reinforcement Learning. And right now we are at the 5th topic, which is regularization. Within that topic, there are 15 questions and answers, and every question and answer is a concept. And these Q&As are divided into 4 subtopics: 5A, which you can see is in yellow color, and 5B, 5C, and 5D in different colors. So we go through each of them as per their difficulty. And without further ado, we move on to the details of the Q&A for this video lecture. So we are at the topic or the video 5B, and which is regularization. And so how does early stopping work, which is a regularization technique, and what are its benefits and limitations? This is a very interesting question, and I would like to give you an analogy before we go ahead. And of course, these are the bullets which we'll be discussing. So the analogy which I would like to give you, this is something called as the law of diminishing returns. So basically, what it is showing is that when the as the total input increases, the total output also increases, and there is a direct relationship, and this is the most productive part. Then the law of diminishing returns sets in. So with the further increase in the input, there is an increase in the output, but that increase is not the way it used to be. So it has diminished. This slope is higher and more than this one, right? So that's the law of diminishing returns has set in, and subsequently, point of maximum yield, after reaching that point, further increase in the total input, as a matter of fact, results in negative returns. So one needs to, as a matter of fact, identify the point of diminishing return. So this has many practical utilizations in real life. Okay. So this is the analogy. This is just the analogy. So what happens in early stopping? In early stopping, what happens is that we would like to prevent overfitting during the training, and this is especially true for deep learning. So what happens is that the model's performance is continuously being monitored using a validation dataset after each training epoch, after each training cycle. So when we see that the performance no longer improves or starts to degrade, so point of maximum yield has set in, starts to degrade, okay, training is halted, and the model parameters, okay, from the best performing epoch are retained. So this could be this one, or this could be this one, point of maximum yield. But remember that the point of maximum yield is achieved with more total input as compared to the point of diminishing returns. Okay. All right. So the point here is that this early stopping work has roots in a certain law. So early stopping basically defines the number of consecutive epochs without improvement, right? Without improvement. So without improvement, otherwise it is going down without improvement, right? And then of course training needs to be terminated. Okay. So basically this of course this works for generalization, and of course the, we are looking for the peak, right? So when we stop the training at the optimal point, when we can stop here, we can stop here, right? This early stopping ensures that the model does not begin to memorize the noise in the training set. Memorizing the noise in the training data is what? That is basically uh, uh, overfitting. Okay, that is overfitting. So let me first explain to you a diagram through a diagram. Okay, the effect of L2, right? And then we'll go through these bullets. All right. So we have so what we see over here basically is the L2, okay, or weight decay regularization, right, for the optimal value of W, for the optimal value of W. Okay. So this is the solid ellipsis over here. These are the contours of equal value, okay, contours of equal value without regularization. And these dotted circles are with L2 regularization. Okay, now try to understand. At the point, this point W dash, okay, or W tilde, these 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 basically competing objectives are at the equilibrium. So these they are at the same, they meet. Okay. So 1 2 3 4, 1 2 3 4. So they are at equilibrium, right? In the first dimension, right? Right. So we see that how these objective functions are increasing. Basically, these are the eigenvectors. So since I have not I've not like explained to you what are eigenvectors, so I'm not going through the wording or the actual concept. So what we can see over here is that W star this W star basically does not increase much while moving horizontally away from W star. But the objective function, right, which we are seeing here, right, it does not have any specific preference for this direction. So this figure basically has two dimensions, dimension one here and dimension two here. Okay, that's number one. Number two is that we can see that this is for the L2 regularization or weight decay, right? And this regularization is for the value of optimal W. So this is an ellipse. You can see this is an ellipse. This is a circle, right? So this ellipse over here, this is unregularized. This is unregularized. It means that it has overfitting. And these dotted circles, this is the regularizer, which is L2, which is circular, right? Which is basically the square of the values. So at this point, W tilde, they are at equilibrium, right? So in the first dimension, which is one, so dimension one, dimension two. In the first dimension, uh, we can see that the objective function does not increases a lot, right? For and we can see that the objective function is very sensitive and is away from W as static. However, the regularizer pulls W1 close to zero, okay. And in the second dimension, this is the second dimension, the objective function is very sensitive and is away from W star. That's the point. So what is the overall impact? The overall impact is the weight decay. Okay. Uh, the position of W2 is as per the W2 which was supposed to be. So the point over here is that we are able to control we are able to control or manage uh, overfitting, right, by early stopping. That's the point. Okay. So let's look at these bullets now. It will make more sense. So training monitoring. So what happens is that in early stopping, the model's performance is continuously being monitored during the training. Okay. And we are looking at the loss, or we are looking at the accuracy. So we're looking at the loss, right, or the accuracy. So by observing these metrics, this loss or accuracy, now we get to know that how further the training should improve, or we should wait for the training to improve. And the improvement on in training is the improvement in generalization. And then, of course, we would like to stop at an optimal point before overfitting begins. So, depending upon how the epochs behave, that optimal point could be this one, or that optimal point could be this one. Now, remember one thing, that the law of diminishing returns has been around for a very long time as compared to deep learning networks. Then is the validation based trigger. So, what is the validation based trigger? This is the decision to stop training, okay, based on a certain performance validation set value. It's not based upon the training set, but it is based upon performance. So when the validation loss stops improving for a set number of epochs, which is called as patience, so that we see that for 5 epochs there is no improvement. So this is called as a patience. So the training halts. So of course this will depend upon the data set also. This helps select the best performing model state based on the unseen data. Okay, not just the training accuracy. So we are seeing that there's no change, no change, no change. 5 times, 5 epochs, no change, then stop. 7 epochs, no change, stop. Whatever that patience could be. Then is the overfitting prevention. So one of the biggest or main benefits of early stopping is that it prevents overfitting. So when we halt, okay, halt the training. When do we halt the training? When the model starts to degrade. Model starts to degrade on the validation data. So what is happening, that it is not learning noise, okay, or it is not learning irrelevant patterns, okay. So this is going to help us, and this is going to lead to better generalization for the unseen data. I hope this makes sense to you. So I would strongly urge you to read the material also for this Q&A. Then of course is the computational savings, not only the computational savings but also the energy savings also. So early stopping will obviously reduce the training time, and it will obviously reduce the computational cost. Why? Because of eliminating unnecessary epochs, because those epochs are just not contributing anything. They are just telling you again and again that the validation is not working, so please stop, please stop. So once that optimal performance is reached, right, this law of diminishing returns can help. So then of course continuing training offers diminishing returns. Therefore, if you stop early, it helps save energy, it helps save resources, and especially for large models, and if you have limited computing environments, right? That's the point. So all right, hyperparameter sensitivity. Hyperparameter sensitivity. So this early stopping depends upon those parameters like patience. Patience is how many epochs, and monitoring frequency, how frequently you're monitoring it. If it is not set carefully, okay, so the training may halt, or you may stop training too early, which will result in underfitting. It is just like you're cooking. Maybe if you're boiling eggs, okay, so if you turn off the heating too early, so you don't have boiled eggs, you have half boiled eggs, right? And if it's too late, you just keep on providing the heat, okay, so the yolk will get hardened, and if you keep on doing it, the egg may actually explode also. So this sensitivity makes it necessary to tune these parameters carefully. Okay, and of course this will require trial and error also. So that's where you need those AI engineers. That's where you need people who have studied, who've taken this course. Okay, so it can require trial and error, and it can require cross validation. So as before, I would suggest that you read this material. Okay, you read the material, and if you're interested, there are more references here. And as I told you before, there's a lot of material here which is not in the textbook. Okay, it's a lot, huge amount of material is not in the textbook. The content, the diagrams, they're not in the textbook. So if you really want to launch your career in deep learning and machine learning and artificial intelligence, I would strongly urge you to look at these references. Okay, and of course, spend time reading them. So, how data augmentation can be used to increase regularization? Now, this is very interesting thing. So, what is actually data augmentation? Uh, this is one example. I will explain this to you what this picture means. So data augmentation, basically what we are doing is the artificially expanding the training data set. So this is the picture of a butterfly which you can see. So we are artificially expanding the training data set using certain transformations, but we preserve the labels, okay, but alter the input distribution. So you can read it, right? So this is the original image, then remove the texture, remove the color, enhance the edges, salient edges, rotate them, and so on. So basically, what we are doing is we are artificially expanding the training data set. So what happens is that by virtue of this augmentation, the transformations, as a matter of fact, expose the model to a broader variety of the examples of same type. So that encourages learning. It encourages generalization. It encourages robust feature identification. It discourages memorizing patterns, okay, specific to that original training data. So that's augmentation. So basically, how we achieve augmentation by applying random or random changes or rule-based changes, and that is applied to the input samples during the training. So for image data, this may include what I have shown you here. In text data, it may involve substituting synonyms or maybe rewording, word shuffling. In audio, it could be pitch shifting or background noise and so on. So what these perturbations are doing, that they are creating slightly modified versions of the existing examples, and the labels don't change. So of course this effectively increases the training data size also. So if you recall, when we studied machine learning as a topic in this course, I we studied the example of a person with varied light intensity, varied light sources, such that the machine was able to recognize the person better than the human beings, right? So we are using those concepts, right? So because the machine looks at a person in a very different manner as compared to we perceive a person. So introducing variability. So what data augmentation does, it increases the diversity of the training inputs. And how this is done? It is done by rotation, it is done by scaling, it is done by noise, adding noise, it is done by decolorization, it is done by edge enhancement, and so on, depending upon the nature of the data. So what this does is that the model is exposed to broader range of examples. So it will have less memorization because there's more variety. So when there is less memorization, then there is less overfitting, right? So it gets better prepared to recognize patterns in different contexts. Okay. So it is like, for example, if a child spends most of the time inside the house, okay, so that person is not going to be, or and in the protection of his or her parents, that child is not going to be tough as compared to a child who goes out, plays outside, hurts himself, falls down, gets up, and so on. So that person is going to have a stronger personality because that person is out of his or her comfort zone. I'm just trying to make an analogy. I hope it makes sense. So with this variability, your model is better prepared. Your means the trained model is better prepared to recognize patterns in different contexts. Then of course, as I've already mentioned, this prevents overfitting. Overfitting is an enemy. So by constantly altering the training inputs, okay, this data augmentation prevents memorization of the original data set because it's always changing. So each epoch presents slightly different examples, and so it forces the model to focus on the core features rather than the data specific noise. So I gave you the example of the child who was looking at his or her mother going to a party with makeup put on. So if the makeup which is put on is sometimes light, it's sometimes heavy, it's sometimes no makeup, and so on. So that of course there are diverse variety of views of that child's mother. So that child is more likely to not memorize but generalize, right? As compared to a child who always sees the mother in the same makeup. Okay. So this approach basically helps reduce the overfitting, and of course this improves generalization and improves performance on the unseen data. So it encourages generalization. So no need to discuss it. And simulate the real world. Augmentation simulates imperfections found in real world, right? Because this kind of a picture is very is unlikely to be taken or made available the second time or the third time. This is not possible. The angle would change, the lighting would change, there could be some other changes also. So this basically augmentation simulates the real world. Okay. And such as a blur or a background noise. And so it basically it prepares the model for practical deployments. Okay. For of course for a wider range of input conditions. So that makes it more resilient to real world variability. Okay. And unexpected distortions also. So getting out of the comfort zone. And of course it will reduce the data bias also. So because there could be skewness in the data set. Okay. So when these diverse samples are generated, so maybe the underrepresented classes or features get their representation also, or instead of guessing it, we can kind of ensure this. So this of course reduces the bias of the model towards dominant patterns in the training data. So it results in fairer, more fair and more equitable learning across all categories. So I hope you have understood this, and there is a lot of material here, and of course there are references also. Okay. All right. So let's move on. So what is batch normalization? Okay. And does it act as a regularizer? So what happens is that as the data goes through the neural network, what happens is that the statistical properties of the distribution changes, which is highly undesirable. So that needs to be taken into consideration. So for example, if you look at this figure, wonderful figure, so what we see is that we studied techniques such as min batch. So the it is divided into batches, and this is batch one. After back propagation, these are the input features, distribution x at the input. Now what happens is that at these hidden layers, the distribution has changed. This is like normal or Gaussian distribution. This is skewed to the right, and this is decaying kind of a distribution. So this is very different. This is not the distribution at the which was at the input. So obviously, when the distribution changes at the hidden layers, the output will be very different. It would not have the distribution which was there at the input feature, which should have been the case. So what we want to do is that in batch normalization, we want to normalize the inputs of each layer. Normalize the input is this is the input. We want to normalize the input at each layer. Input at each layer, okay, so that the mean is zero and the standard deviation of 1. So how it is achieved? It is achieved by uh, for one for the standard approach is that you subtract from the actual value the mean and divide by the standard deviation. But I'll show you that we'll do more than that. So this phenomena which I just mentioned to you, this phenomena, this is called as the internal covariate shift. Very kind of difficult. So what happens is that the statistical properties of the input data, this is the input data, statistical properties of the input data change between the training and the testing phases. That's the problem. And when it occurs, when the distribution of inputs to a layer changes, okay, during training, and of course it will not have the desirable impact. So what we need to do is, so how we achieve it. So that taking care of this covariate shift is called as batch normalization. So what are the steps which are applied
compute the mean, okay, and the variance of the activations for each min batch. This is batch one, then of course there'll be batch two and batch three and so on, and normalize the batch using these values, okay, and then apply a scaling, okay, and scaling is and of course then apply a shifting to preserve the model capacity. We have discussed what is meant by model capacity, and this is done for each feature independently. For each feature, this is done. So this is one feature, this is second feature, so this is done for all of them, right? So so the in a nutshell, basically, if you want to be an AI engineer or you want to be a data scientist who, as a matter of fact, have the largest growth projected growth rate and very high starting salaries. So you need to have good statistical background, good experimentation background also. Should have done things by hand, okay? And so that's so this in this course, we you will be doing a project also of training a deep neural net, spending not more than 2 hours of training on it. So we'll talk about it anyway. So before we go to these bullets, right? So these are the operations which are performed. Okay, so this is the normalization. So notation from left to right. This is the kth feature column of the data. Kth feature column of the data. Okay, and this is the hat. This is hat. Okay, normalized data, right? And you can read them all of these things, right? So this is how the normalization takes place. Okay, so you should have a good understanding of the statistics, corresponding statistics. All right. So let's move to the bullets. Normalization layer. So what is the normalization layer? So the layer, okay, that normalizes the activations of each mini batch during training for each of them. So what it does, it adjusts and it scales the inputs. These are the inputs, scales the inputs, adjusts them to have a consistent mean and variance. And that mean is zero, standard deviation is one. And what it will do, it will stabilize the learning, okay, and it will keep the input distribution more or less consistent, more or less consistent throughout the training. Throughout this training, it should be, it should remain Gaussian. Slight shift or something change, this is not acceptable. This is skewed to the right. This is, so this is not what the data is. I believe you understand this, right? And then is accelerated. So we were looking at this. My apologies. So then is accelerated training. Okay, so this is accelerated training. So when we standardize the layer inputs, batch normalization, this is batch normalization which we're doing, okay, reduces the sensitivity to initial weight values and the learning rate. So the impact is reduced. It's not eliminated, it's reduced. So as a consequence, the convergence is fast. Convergence is fast basically. So the movement on the gradient descent is quick, and it allows for higher learning rates. Okay, it means it takes less time, and of course this reduces the number of epochs. So instead of, say, like, I don't know, x epochs, so x dash epochs are used because each epoch takes less time. Okay, so optimal performance is achieved quickly. Then is internal covariate shift. So what these batch normalizations, okay, they take care of the internal covariate shift. Okay, so what is that so the problem of changing input distributions across layers as parameters is updated. Okay, so these things are taken care of, these at the input. Okay, all right. So now when this input distribution is stabilized, okay, this is not stable, it improves the gradient flow through the network. Okay, so that allows now see this distortion, so to say, we would like to, when we kind of control it, it allows for deeper architectures. And when the architectures are deep, that it kind of leads for efficient optimization. So this course is not at that level that we go into all those details. This is a fundamental course. All right. So now we know that this acts as a regularizer. Yes, batch normalization has a regularization effect, although that's not a significant, but it is there. Okay, and what it will do is that the noise introduced by min batch statistics, This is the noise, this is the impact. The noise shifted, skewed it. Okay. uh, these techniques help reduce overfitting. Okay, but it is not a substitute for the stronger regularization techniques like L1, L2, or dropout. So if you look at the question statement is was does it is it acts as a regularizer. Well, it acts. It is not a regularizer. It acts like one. So the true regularizers are L1, L2, or dropout. Okay, those are the true regularizers, and it is widely applicable. It is widely applicable. Okay, here we are. Widely applicable. It is used across many deep learning architectures. See convolution neural networks, recurrent neural networks, transformers, because it improves the stability, because it improves the performance. And initially, this was designed for feed-forward networks, as it seems over here. But it benefits in training and speed. Okay, and nowadays, like it is, we have used it for in back propagation also. All right, so let's move on to the next interesting concept Q&A. So which is, you can read all of this here present here. Okay, try to understand. Here are the references, and I said again, you will find many things over in this content which is not in the book. All right, so what is bias variance trade-off in deep learning? So trade-off means that kind of a balancing act. You let go of something and you gain something, and you gain something and you let go of something. So that's a trade-off. There's nothing to do with business or economics. All right, so that's a trade-off. So what is bias variance trade-off in deep learning? First of all, I'll show you a picture which will make it clear, and you will understand that what is meant by how to visualize bias and variance. Now let's take a look at this. Like maybe this looks like a target for shooting, for practicing. So this is probably the perfect situation that the variance is low. Okay, and the bias is also low. Variance is the distribution across the average value. So all these things are grouped together. So the variance is low. This has a high variance, lot of spreading. This also has a high variance, lot of spreading. So variance should be low. Variance is also low here. Grouping is there, but it is just missed the bullseye or the actual target. So this is best. So low bias, low variance, perfect. This is the best. Then is the next one. This is probably depend upon the application. So variance is low, but just miss the target. Over here, bias is low around the target, but a lot of spreading, and this is just not very useful at all. Okay. So what we were looking at was bias variance trade-off. Bias bias variance trade-off. So the point here is that if you try to improve bias, then maybe the variance is affected, and the other way around also, you try to balance them out. So what happens in deep learning is that bias variance trade-off, okay, is a fundamental concept. All right, and of course that affects and that describes the relationship, okay, between a model's ability to generalize and performance on training data. So basically, there are two prediction errors, bias and variance, right? So this that kind of suffers from both those errors. Now, where do these errors come from? So bias error is introduced by approximating a complex real problem with a simpler model, because real life is very complex, right? And everything cannot be modeled. And when we try to model it, maybe that model is achieved by those weights and then a neural network. So that may not result into a model which is actually representative of the actual process. So that may result into a simpler model. Like say for example, there's a lot of non-linearity in life. So a linear regression is a simpler model and it results into underfitting, and it's not very desirable. So that's the bias error. So if the bias is if you have a high bias model, okay, then it may fail to capture the underlying patterns. Of course, that will lead to underfitting. Now, if you look at variance, right, the error is caused by the model's sensitivity. Model is very sensitive to small fluctuation in the training data. So what will be the outcome? If the variance is high, it will perform well on the training data, but poorly on unseen data. And of course, that results into overfitting, which we are trying to avoid through regularization. So what is the bias error? What is the bias error? So bias error happens when the model makes, now model is not something independent or can think, right? But as a consequence of those assignment of weights and gradient descent, uh, the task is oversimplified. Okay, and when the bias is high, it leads to underfitting. And then when there is underfitting, the model of course fails to capture the intricate or important relationships or patterns in the data. So what's going to happen? Poor performance for training and poor performance for test data set. Because if the performance is poor for training, right, then of course the performance is going to be worse for test. That is obvious. Now let's look at the variance error. So when does the variance error happens? When we have discussed it, basically it results in overfitting. And of course, when overfitting, the generalization is also low. Then is the model complexity. Model complexity. So as model complexity increases, bias decreases, variance increases. Okay. So this again we are back to square one. So if the model is simple, low complexity, it may underfit. But if the model is complex, it may overfit. So what is the trade-off? The trade-off is a model with the right complexity to balance between both errors, the bias error and the variance error, right? So what are the risks of underfitting when the model is too simple, high bias, right? And poor performance across all data set. So what the regularization can do, it can help reduce underfitting by enabling the model to capture more complex relationship, and overfitting to be techniques like dropout, early stopping, they can prevent or mitigate overfitting, that we have discussed in a lot of detail. All right, so this we have done. So let's move on to the last concept. How do regularization techniques affect bias variance trade-off? So we are not letting go of this concept. So let's look at this wonderful diagram here. Okay, let's discuss this. So what we have this is the training of the model, and this is the error, right? So high bias is underfitting, which we have discussed a lot, and high variance is overfitting, that we have discussed a lot. So we are looking at this part, low general error. Low, basically this is the trade-off, okay, and this has the best accuracy. Now, when is the best accuracy? Okay, this is the general error. So general error is desirable. This is this we have this axis, we have error. So we are looking for this thing. Error should be minimized. General error should be minimized. This is what we're looking for. And as as the variance increases, the error increases, and we have overfitting. Okay, and as and of course as with this progress of model, as the bias decreases, okay, so we are looking for that sweet spot. This is the sweet spot we are looking for. Okay, so that has the best accuracy. You can see that these data elements, they are not included in at all. But over here in overfitting, they are taken part of it. So this is kind of a simplistic. This line should not have been with a curve. This line should have been straight like this. Okay, and we can see, it's very obvious. We can see that the relationship is almost quadratic. It's kind of quadratic, and this line is linear. So this is underfitting. A linear a line cannot represent or cannot recreate or cannot be made equivalent to a linear is not quadratic. Simple as that. So okay, so what we want to do is, so how regularization affect bias variance trade-off? It reduces the variance. So techniques like L1, L2, and dropout reduce the variance, and when they reduce the variance, of course, that results in underfitting. I'm sorry. That just a moment, please. I'm sorry, I picked the wrong item. So uh, reduce the variance, and as the variance is reduced, overfitting is limited. So that's so L1, L2, and dropout achieve this. And they also say, and what else they do is prevent learning from noise or prevent learning from outliers. Okay, so as a result, the performance is improved for unseen data, and it stabilizes the predictions. So one was the variance, then is the bias. So regularization techniques increase the bias. So that bias by simplifying the model. So the model may not fit the training data perfectly, okay, because regularization discourages overly complex. However, there's a trade-off. The trade-off between intentional is that trade-off is basically intentional to improve the generalization. Of course, that may affect the accuracy, but it is like a controlled crash, so to say. Controlled crash as a aircraft carrier lands, so to say, within double quotes on a as a aircraft lands on a aircraft carrier, which is basically a crash, but is controlled. So then is improves generalization. Of course, that's the objective. So when we balance bias and variance, the regularization helps generalize better to new unseen data. Okay, so it prevents memorization. Okay, and of course it encourages learning, which is critical for real world deployment. And by controlling variance, we also control the complexity. Okay, and how it is done by penalizing large weights. And you remember that in L1 and L2, either you set the weight to zero or gradually decrease them. So basically, the focus on simpler, generalizable patterns. And then is the technique sensitivity. So, what is technique sensitivity? Now, different regularization techniques impact bias and variance in unique use. They in their own way. For example, L1 promotes sparsity, okay, because you set the weight to zero. L2 offers smooth generalization because it never actually sets the weights to zero but decreases them. And dropout introduces the noise. So you play with these techniques as a tuning parameters, okay, and then you look at their effect on the bias and variance, and then as per the model architecture and data, so as to have a working system. You see that this is a kind of a this is quite complex, and you need to like control it, tune it, and of course this is not only complex, it's expensive in terms of the requirement of GPUs, requirement of the energy, space, and people. So this requires a lot of understanding and control. All right, so that's all for this subtopic. Thank you.